This video is type 4 of KSP reactions, selective precipitation. So this one's going to actually be an application of the common ion effect, which kind of gets intertwined in a lot of different things. But let's take a look at this problem. We have a solution contains 4 times 10 to the negative third molar of calcium nitrate and 2 times 10 to the negative third molar of barium nitrate. Okay, if sulfate ion is gradually added to this solution, which will precipitate first, the calcium sulfate or the barium sulfate? So in other words, calcium sulfate looks like that's rather insoluble. Barium sulfate is rather insoluble, but it looks like the barium's even more insoluble than the calcium sulfate. So I think that would precipitate first. Okay, if these two had the same concentration, the one with the lower KSP would precipitate first. If these two had the same KSP, the one with the higher concentration would precipitate first. So it looks like the calcium is a slightly higher concentration, but the KSP for the barium sulfate is much lower than the calcium sulfate. So my guess is that's going to be the determiner, and that the barium sulfate would precipitate first. In fact, if this were a multiple choice question, I'd be very confident with that, and that would be my answer. But I'm going to go do a calculation of each one, because some frequently you're asked to do this in a qualitative sense, make a prediction, but it's quite frequent that you're asked to quantify this too. So it says, what concentration of SO4 is needed to begin precipitation? What concentration of SO4 is needed to begin precipitation? In the one that needs the least concentration to begin the precipitation, in other words, you have to add the least SO4, is going to be the one that precipitates first. So I'm going to handle this like a common ion effect problem. I'm going to say SO4 breaks into Ca plus 2 and SO4 minus 2. I write my KSP expression. Concentration Ca plus 2 times concentration SO4 minus 2. And without doing an ice box and working that out, I'm going to say, oh, my concentration of Ca plus 2 is in a 1-to-1 ratio with the CaNO32, and that is 4.0 times 10 to the negative third. All right, so this is a mixed solution, but it's all combined, and we still know the concentration there. Okay, and we don't know X. We're trying to figure out how much X we're going to have to add. So if we know the KSP, we know the calcium is 4 times 10 to the negative third, we can solve for X, and it's telling me the amount of X we would have to add to get to a precipitate would be 0.015 molar. We're going to take the same approach with the barium sulfate. Okay, and looking at that part of the solution, get the KSP expression, and the barium is 2 times 10 to the negative third molarity, which is a molarity of barium nitrate and also the molarity of the barium. We're trying to figure out X, or how much sulfate needs to be added in this case. So again, it's like a type 2b, the common ion effect, where we know the KSP, 1.5 times 10 to the negative ninth. We know barium in this case is 2 times 10 to the negative third, and we're trying to solve for X. We do the math and we get 7.5 times 10 to the negative 7th, which is much lower than this right here. So when my SO4 minus 2 concentration gets up to 7.5 times 10 to the negative 7th, the barium is going to start to precipitate. Okay, it's not going to precipitate calcium until we get to this 0.015 molar right here. So we answered the question, which one precipitated first? The one which needs a lower concentration to precipitate. We answered what that SO4 minus 2 concentration would be here, and we answered what it would be here. What's the use of this? Let's say you have 2 pretty insoluble things with calcium sulfate. You can still separate the calcium from the barium in this solution. What would I do? I drip by drip add the SO4 and gradually precipitate all the barium out, leaving the calcium behind. So this gives you a means for separating calcium from barium in a solution. Even though they're both insoluble, this one's much more insoluble, so it allows you to separate that. Kind of like if you were going to take 2 things that had relatively high, two liquids that had high boiling points, but one was significantly higher than the other, then you could gradually raise the boiling point and you could boil off one first, and then you could boil off the one with a higher boiling point second. So you could separate those two things. So this allows for means of separations of solutions with this selective precipitation. Note the use of the common ion effect and this problem. Thank you.